top this fucking class.
Come again? Hello? Joel, can you hear me?
Yes, I can hear you. Sorry, I think I was trying to check if we were having problems.
No, I was asking the figures you are trying to compare on the urban residence. Which
Yeah.
two figures are you trying to compare?
It looks like they said this is hacked. I don't know whether we can change the link, or because we are getting a lot of interactions.
Yes, I think I've removed the individual from the call.
Okay.
Yes.
So are we good to go now?
Yes, proceed, please.
Okay. All right. Stanley, you can ask your question now again.
Yes, I wanted to know the two figures you are using to compare the depression on the urban.
Yeah, so we are using this figure here, the odds ratio, not the confidence intervals. So here, somebody says that the odds of depression was more likely to, so holding all other factors constant, people living in urban areas are more likely to develop depression than those who are not living in urban, right? And then I was mentioning that if you say more, like this type of conclusion is good for maybe your conclusion part, or maybe part of your discussion, but it was always good to put how much more likely. So in this particular case, if it is 1.32 times, you can say that it is 32% more likely to develop depression than those that are living in the rural area. So it's always important that you understand what the level, what is your reference level, so that when you are doing the interpretation, you are much you are much clearer. Okay, I hope that
Kindly
helps.
circulate the video at the end, circulate this video. We try to revisit it.
Yes, the videos are usually saved and circulated, so you would receive you receive that. Okay. Lindo said greetings from Iswazini, patient advocate and youth mentor. Sapa we live. Okay, that's just a comment introducing. Is it possible to specify the reference group in R? I think we've talked about this. Can you please also tell us about using get summary for getting ready tables? There are so many R packages for summarizing, and that is one of the things I love about R, is that there are so many packages that does the same thing. So yes, you can use get summary, and it's possible you may even be able to tell it to report just the odds ratio in that nicely generated table. Yes, so any package at all that is still able to produce these summaries for you, it's your preference. You have a lot of options in R to use whichever package that you want, as long as you understand what is being reported so that you can interpret it accurately. Okay. All right. Is there any other questions before I move on to the next concept? If we want to model age as a continuous variable, how would we do that in R? So if it is continuous variable, then your data has to just be in that continuous nature. You don't have to categorize it, and just plug it in the model. So that one, you don't do anything. You just put age there. Instead of age group, you just put the age, and then it will give you just one value for for age, and you can interpret it as any unit increase in the age would lead to whatever that odds ratio is in the reference compared to the reference group. So the interpretation is just the same, except you just say one a unit increase in this will lead to that. Effects of interactions, yes, effects of interactions can also be done easily. You just put the times. So if, let's say, I want to add an interaction between, if I want an interaction between age and sex and age group, I'll just put a times, a times on it. I think I can show the R code so that we can do it together. But before I do that, Karim, your hand is up. Just go ahead, and then I set up my R. Karim, go ahead.
Sorry. I was struggling to on my mic. Mike, I wanted you to go over the interpretation of the odds ratio when it's less than 1. I didn't quite get that side well. Thank you.
Okay. So when it is less than 1, when it is less than 1, you can just take 1 minus that value. So in that particular, let's say if I'm using, we were using the Richard. So if you pick the Richard, it is 0.689. So let's say 0.69. So take 1 minus that. So once you take 1 minus that, that figure, you get a number which is in like 0.13, and you multiply that by 100. So when you multiply that, because when you do the subtraction, you get negative. And that is why we say that it has a lower, you have to use the word lower when you are doing the interpretation. But if you subtract 1 from, let's say, urban, if you subtract 1 from urban, you get 0.32, which is positive. So when you multiply it by 100, you would get 32.2%. So when you are interpreting urban, you can say that the odds of living in an urban area, the odds of getting depression when from people who are residing in urban areas is 32% more higher than those who are living in the rural area. Okay. And then if it is the negative version, you just subtract 1, you get negative. Ignore the negative, but when you are doing the interpretation, you just say that it is lower than the other group.
Okay. Okay. Thank you.
Okay. All right. So let me share my my R screen, and then we can. Oops. I hope you can all see my screen.
Yes.
Okay. Yes, and I believe you have. I believe you have all received this code. So the first line that I have here, remove list ls. In case maybe I was using my R before, there will be so many variables in the environment. So because of that, I always start by removing everything so that I don't get confused. Maybe I have a variable that is named the same way as some of the variables that I'll be using, and I'll get confused. So I run this line of code anytime I want to start running my R. So when I run this, any object that was here would be gone. Okay. And then I have this line of code that sets my working directory to wherever I save this file. So I save this file in a folder where I have my data, and then I have all the other programs. So I want R, I don't want to go and copy the path and come and paste it here, you know, in my R code. So what I do is that I will just use this command. You don't have to know how to get it. You can always copy this and paste it in your R code and use it anytime that you want. It always works. So you just start from the remove to the graphic.off, and then you can always apply this. So what this does is that it just sets my working directory for me. Okay. So now if I want to see what is my working directory, I'll say get working directories. And then you see that I have a very long path. I have a very long path here, and I'm not interested in copying this and pasting it in my console anytime I'm reading my data, so that it's very easy for me. In the folder where I saved my file, I have, so again, this also means that if you also pick all the files that were shared with you, if you put it in one folder, all you need to know is just open the R file, and the moment you start running, you can also run everything that I am running from my side without having to go and copy, change directories, everything. Yeah, you avoid all of that. Okay, so remember the name of the data set was the DHS. That is the name that I called it. So when I run that, I get my data is read into it. So you can see that now an object have showed up here, which is called the DATS, and that is the name of my data. Okay. The dimension, so I can run the dimension. You can press control, you can put your cursor on line 12 and just press Control L. If you press Control L on your key, it will run that particular line. Okay, and then the cursor moves to the next line. I can press Control L again, and then it gives me the summaries, the first few columns of my data, which is what we had in the slides. Okay, our favorites. English Premier League team, Arsenal is here. So we run Arsenal. Okay, there is also Cable Extra, which I like to use. Yeah, Dennis, I see you. Cable Extra. And then remember we have, so the table by, we can run this. So here we have explained what's the depression, which is our outcome in the data. The gender is there. And then we can add all of the options that we want. So we can highlight all of this, Control Enter, and then when we want to see the results, we run summary table, and it gives us the descriptives in our console. Okay. In case I want the other options, so remember I told you that some of these options you can change them by yourself. The function is table by. So you can do a question mark, table by, okay? And then it will tell you everything about the package. You'll see it's displayed in the help console panel here. And it tells you everything about that package. You can, if you want options, so usually all the other options is in the table control. So I can click on this table control that has come, and then now you have all the options that you can put there. Remember I told you that if the total column here, the total, if I don't want to display it, now I can see that if I don't want to display it, I can use this option here. So what I'll do is that I'll come and add total equals false. So the default is true. That is why when we run the package, it gives us this column. But if we don't want to produce this column, then we can set it to false. It's either you can type false in full, or you can just type F, capital F, which means the same thing. And this time when I run, and then I run the descriptives, you see that the total column is no longer here. Okay, so it means that I got rid of it. So there are so many options that you can just study about this. Remember, I also mentioned that for the categorical statistics, I'm saying that for categorical variables, report if there are missing values, report the number of observations, and report the row percentage. If I don't want the row percentage, but I want only the column percentage, then I'll remove this row here. You would see it as the default. Okay, so I'll just say produce the count and the percentage. So let me delete that. When I run again, remember now it was this plus this that is giving me 100%. But now if I change this and I run, then it's going to make this and that is the one that will be 100%. Okay, because I have said that I want only the count and the percentage. But the count and percentage, when I do it this way, then interpretation is it's not interesting to interpret this proportion percentage. That is why I report the count row percentage here, so that I can interpret it as my prevalence. I can see this one as the prevalence of depression amongst females, and this will be prevalence of depression amongst males. Okay, there are so many options. The package can do even survival. If you want to fit a summarize the survival data, and you want to report the events, it has so many other options. It's a very nice. The p-values that are reported here, you can use so many. If you want you want it to report non-parametric p-values, or you want it to report parametric p-values, there are options for you to select to make that decision. So if you want, so you have a lot of tests here. You can do Crystal Wallace, you can do ANOVA. There are so many tests that you can produce if you do that. Okay. Any questions so far? Anyone with any burning questions? If everything is good, just give me a thumbs up.
Sorry, I have a question, someone.
Okay, Lene, you have a question? Go ahead.
It's Dennis, sorry. So
it was Ben. Please go ahead. The person who had a question.
does it mean that you don't have to, you can get the p-values automatically from using this package? Because the others, sometimes from the results you were showing previously, we had lots of p-values. Now, let's say you want an overall p-value. If it was a categorical p-value, you don't have to use the likelihood ratio test command in R. You can use this Arsenal package. I don't know if that makes sense.
You mean comparing to the logistic results?
Yeah, exactly. Like now, when you are doing like, let's assume this sex was not sex, it was something like socioeconomic status with many categorical.
Yeah.
So in there, that when you run some analysis, sometimes you get many p-values, and sometimes I can see here we have one p-value. So when does it happen that we have many p-values, and at times we have a single p-value?
Okay. All right. So for this Arsenal package, the p-value that it's reporting, it is just fitting a model one, looking at one at a time. So depression will be paired with sex, depression with age, depression with wealth, etc. So here it is not adjusting for anything, unlike in the logistic regression. So remember the logistic regression, when we are doing our interpretation, we say given holding all other factors constants. Okay, so those ones are adjusted coefficients that we are reporting. So the Arsenal package is not doing that. The Arsenal package is just doing univariate analysis. So it's just picking depression and sex, depression and age, depression and what like that. But when you fit a logistic regression, the adjusted one, sometimes you would find that the p-values are significant for some of the levels, but they are not significant for other variables. And so you'll be wondering, so does that mean that if I want to say something about, let's say, age is significant for maybe 50 to 59, 40 to 49, but maybe it's not significant for 30 to 39. Okay, so in that case, would you say that the variable age is significant or not? You know, that becomes complicated. But one quick way to know that is that if a variable has even one of the levels, even one of the levels is significant, then overall that variable will still be important. Okay, it is only when none of them is significant that is when you have to start thinking about something else to do, like maybe let me do a likelihood ratio test to confirm or things like that. Okay, but if only one of them is significant, then it is when you perform the overall test, you still find that that variable is significant. Yes, Marlo, your hand is raised. Please go ahead.
You can try to interpret male and female on these figures you have displayed here. We hear how you have interpreted it. I see the connection.
Okay, so here I'm saying that remember that this is gender, male, female, and this is depression, yes or no. So I'm looking amongst the females. What is the percentage of females who have depression? So here is 2.9. So I'll say that 2.9% of females have depression. Okay. And then 2.4% of the males also have depression. So if I'm interpreting this p-value, it is not significant. So I can say that
Thank you.
it is not significant because the proportion of the prevalence of depression between males and females is not significant. And you can see from the value 2.9 and then 2.4, statistically, they are not significant. Okay. All right. So I hope the question on the variable selection thing is clear. But we have a section where we can actually go into it to tell whether our model is doing well or the model is not doing well. Because it's not about just throwing anything at all that you have as a variable into your model and just start interpreting. So there are other things that we need to check before we even start interpreting our results. But at least now we know how to interpret our results. We can go on to the next section later on. So let's go through. Somebody talked about interaction terms. So the interaction terms, so assuming that I want to look at the interaction between hypertension and sex, okay? Then all I need to do is that I'll just put plus sex times hypertension. So I'll just add this interaction term to this, okay? Another way is, so assuming that, assuming that I don't have all these other ones in my model, I only have sex plus hypertension plus sex and then interaction with hypertension. Okay, so maybe this is the model that I want to run. All right, so I can run this. I didn't run the response, so let me run it here. This is where we were defining the new y variables. Okay, so now I go back. So I run this and then I run that. So when I run that, so you see that the results is I have the intercept, I have the gender, which is male, I have hypertension, which is yes as the reference, then I have the interaction. Okay, so this coefficient would represent the interaction. It's not significant. So anytime you have a non-significant interaction, it means the interaction is not important. One of them is not moderating the other, so you can remove it from the model and just proceed with it. Now, a simpler way is that in R, if you want to fit an interaction model, you can remove the first two lines, like sex and hypertension, and just have sex and hypertension. When you run this, you will get the same results as the one that I ran. You still have the coefficient for male, coefficient for hypertension, and then you still have the interaction term. The reason is that you cannot have a model that has interaction without its fixed effects. Okay, so even when you remove the fixed effect there, the moment you have added the interaction, the software will make sure that it also adds the fixed effects in the model. All right, so you can, so anytime you want an interaction and you don't want to make your code so complicated by typing all the fixed effects and then all the individual effects and then all the interactions, you can just you put only the interaction in the model and just run it, and it will still produce all the fixed effects, the individual effects, as well as the interaction effects. I hope that is clear as well. Okay. Anything somebody wants me to run from this before I switch back to the slides? Anything you went through the code that was not clear to you? Because almost all of them are in the slides. Yeah. Stanley.
Hello. If you would interpret this hypertension here on the coefficiency, which figures will you be comparing here? Because I'm only seeing males and no females. If you are to compare hypertension, which figures will you compare here to get your report?
So if you are reporting, you report the one here. Have you seen this for hypertension? So you report for hypertension differently. You also report for male sex differently. You don't put them together. So I can interpret this. So here, remember, it is a logistic. So before I interpret it, I have to take the exponent of that. Okay, so let me take the exponent of that. Okay, let me run the library. Where is the library? Epi library. Okay. Then I can model 2. I need to run this one. Okay, it doesn't work for in the right click here. Let me remove the interaction term. The package is not supporting interaction, so let me remove this. Run this. And then I display the okay, let me do this. Okay, so can you see these results? So you see it. So if I'm interpreting this model, I'll focus on the hypertension here, right? So the hypertension, the odds ratio is 3.89. So when I'm interpreting it, my interpretation will be the odds or the likelihood of getting hypertension, of getting depression for people who have hypertension is 4 times that of, now the comparison comes in, that of those who do not have hypertension. So the comparison would always be between whatever is used as the reference. So that is why we talked so much about the reference. Here we have only sex male. So sex male, has 2 levels, male and female. So it has given you the value for male. That means that the female is the reference. So when I'm doing my interpretation, I would say that the males have the males have a lower risk of getting hypertension compared to what the females, because the odd ratio is less than 1. Stanley, is that clear now? Obviously, whilst holding all the other factors constant. Yes, Stanley, go ahead. Okay, good. So you are good now. So always the comparison, we are always comparing it with the reference level of that particular variable. So it's important that we remember what the reference level is for each of the categorical variables. Very, very important. All right. So let me go back to the slides. Okay, we are not doing very well with the time, but yeah, but it's important to understand very few things than receiving so many things and not understanding anything. All right, so I'll rather take my time, take all your questions, understand the basics, and then even if we are not able to complete everything, when you read or when you study them on your own, you would have much deeper understanding than if we just rush through everything. So it's still fine with me that we are going at this pace. Okay, so I did mention that before we go ahead to interpret our results, it's always important to know that we are interpreting the result for the best model or the very good model. Okay, and so in statistics, we call that a model diagnosis and the assessment. So we are going to diagnose our model because I can fit a model by adding only sex, by adding sex and age. I can add so many different combinations of the variables into my data sets and I'll get different models. So there are so many models that we can fit with just even this data that we have that has only 12 variables. I think 10 independent variables. There are about 10, but we can fit 2 raised to the power 10 different types of models just on just this particular data. So it's important that we understand, okay, which amongst all these models, which one should I work with? Which one is more important? So first of all, we need to diagnose the model to see whether it's really a good one before we go ahead and then interpret it. So one of the ways to assess a model is called model diagnosis. So model diagnosis is just making sure that our the model that we want to interpret it's a good one, it's a good fit, it's fulfilling all the assumptions that are made by the logistic regression. So there are several diagnosis techniques. One of them is, we call it residual analysis. You can also do what we call a goodness of fit test. And one of the goodness of fit tests is called the Hosmer-Le test, which we will look at. They all tells you whether your model is really a good fit. If I have more than one model, so this first one, I can just have my model, maybe it's just one model, and then this, maybe that is the one that I have decided I want to fit, but I want to be sure that it is doing a good job. Okay, so I'll do a diagnosis of that model, and if it is not good, then I'll look for another model. But assuming that I have several models, several different models that I am considering, then I can do the assessment of model fits so that I can compare how all these models are doing, and then I'll decide based on that no, I think this one is the best one. Then I'll go ahead and interpret that model. So that is the other assessments that we are going to do. So we are going to consider both. If let's say I just have one model and then I want to be sure, I want to convince myself that this logistic regression that I have fitted is good enough for me to proceed and interpret my results. So just some concepts for residual analysis. Residual is just your estimated errors. So every model is wrong, but most of them are useful. So the models are not always accurate, but they try to, you know, predict or explain your data. So your residual is after I have fitted my model, I can predict my probabilities and then compare that with the observed data, the data that I have. Okay, so I have my data, which is what I have observed, and I have their probabilities. Then I have also the predicted probabilities that is coming from my model. So I compare my data with my model, and then the difference in those probabilities is what we call the residual. Okay, so residual, or just errors that you have made by the model. So you take the observed minus the predicted probabilities. And often residual is not adequate because of the variance of the distribution of the mean for Poisson, not that important. But because we have mentioned that the mean and the variance of the Poisson of the binary data or binomial distribution, that if somebody tells you that the mean, which is the probability, is pi, then I know the variance. The variance will just be pi times 1 minus pi. This we have said when we started the regression. So it means that when we compute the residuals, because we said the residuals may not be handles non-constant variance. One of the assumptions that we made about the linear regression is that it assumes constant variance. Okay, so we have another type of residuals where once we have taken the difference between the observed and the predicted probabilities, we are going to divide it by the variance of the data, of the variables, or of the response. So we divide that residuals by its variance. We call that the Pearson residuals. So Pearson residuals is just our normal residuals divided by the square root of our variance. Okay. Now, when we do that, it means that we have standardized our residuals. So anytime you have some differences where you divide by the standard deviation, then the distribution of that gets closer to the normal distribution. So it means that we can use that to diagnose our model, that anytime we compute our residuals and then we divide by the standard deviation, then the Pearson residual should be something like a bell shape because it's a standardized one. So it means that it's supposed to look like a bell shape. All right. So it means we can use that to tell whether our model is actually doing well or not. So we would compute our Pearson residuals, and then we can do a normal plot. And then we hope that that distribution will be normal. That plot can also tell us whether they are outliers or not. There are formal ways of telling whether maybe there are outliers, but these are not very common for binary data, much commonly for continuous data, but they are also applicable for binary data. Stanley, is your hand still up? Is it an old hand, or you have you have a question? Stanley, your hand is still up. Do you have a question? Okay, so the key message here is that we want to see whether our model is good or not. So what we do is that we compute the Pearson residuals, and then when we plot the Pearson residuals, we want them to look like a normal distribution. All right. And then we can also test, use the KK plot to test whether indeed it follows a normal distribution or not. And then if there are outliers in the data, we still be able to identify that from that plot. Okay, so how do we do that in R? So first of all, we would get the fitted probabilities. Okay, so the fitted probabilities, I'm going to get the model that we fitted is called model 2. Then I use the $sign, and then I'll get the fitted values. Okay, this gives me the fitted values. I can also get the Pearson residuals directly from R. I can just say residuals into brackets. Then I mention the name of the model that I want to compute the residuals from, and then I'll tell it which type of residuals. There are different types of residuals, but here I'm interested in the Pearson's residuals. So this would give me the Pearson's residuals, which is just the difference between my observed probabilities minus the probabilities that I get when I fit the model. Then I divide by the variance, okay, the standard deviation of the variance. And that is what the Pearson residuals gives me. Then once I am done, I can just plot. One of the diagnosis plot is that I can plot the fitted values from the model versus the Pearson residuals. So I just say plot fitted values and then Pearson residuals. Now this diagnosis plots, when I do the plots, we see that they are almost like two. There is one here and there is also one here. It's just because we have a binary data. If it is continuous, then it would be scattered all over the place. So when I look at this plot, what I want to see is that I want to see that almost all the residuals are very close to zero. And they are all scattered around the same area. Okay, so there should be something like this. All right. They should follow something like that. Florence, when fitting the difference models for diagnosis, do we also look at the significance of the individual variables or not? So here we are assuming that we have done all the model selection. We have decided that, okay, this is the final model. It has all the significant values, and then I'm ready to interpret it. Okay, so you have already done all of those stages, which we are yet to come to. How do I decide whether my model is good or not? We'll come to that. But this step means that we have already done all that step. So we know which variables are okay. And then once we make a determination, we now want to see whether the final model that we have it's a good one. And that is when you start doing this diagnosis. Okay, so when I look at this, it is not bad apart from this side of the graph. Okay, I see that most of them are, especially these ones are zeros. These ones are almost, because I have 0 and 1. So 1 is representing that group that has the 0 outcomes, and then the other ones, like I mentioned, it's not always good for binary outcomes. But I'll see that the model is not doing so. It's not doing so good because I still have these groups coming from here. But these are visuals. I'm just using my eyes to make that determination. And that is why sometimes it's good to use other formal tests to confirm whether whatever you are getting from your graphs are telling you the correct story. Okay, so that is how we do that. Another way to do the same graph, so you see that the graph that I generated here, I did it myself. I extracted the fitted values, and then I also extracted the Pearson residuals. Then I did the plots by myself. So I did the plots, and then I put the line here, the horizontal line, to see whether all the points are around 0. Okay, so that is me doing it myself, but I can decide to let R do it for me. without going through all those steps. So how will I do that? I can just say plot, put the name of my model, and then add this command, which is equals to 1. Okay, so when I say which is equals to 1, then it gives me the same type of plots that I was doing manually. And then again, you see this cloud of points. That seems to be like outliers because they are not closer to this other one. So at least the residual plots can also help me to say that okay, it looks like these people are outliers. Okay, but then majority of them are still very close to each other. Still very difficult to tell whether the model is doing very well or not. Okay, but we have to, that is why we need to apply other formal tests to see whether we can be convinced or concrete that this model is doing well. Okay, then here I use which is equals to 1. That means that I can also do which is equals to 2, or which is equals to 3, which is equals to 4. So in R, automatically, some of these diagnostics plots are already inbuilt into the package. Okay, they've already done that because they know people will still want to do diagnosis. So it's already done. So when I am interested in getting the fitted values plotted against the residuals, I will just say which is equals to 1. I can also do which is equals to 2. Okay, when I do which is equals to 2, it plots the standardized Pearson residuals, a QQ plot of that. And the QQ plot is a plot that tells you whether your residuals are normally distributed or not. So remember, we said that once we use the Pearson, the standardized Pearson residuals, then we expect it to be normally distributed. And how do we tell from the KQ plot if it is normally distributed? They must be on the same line. Okay, they must be on the same line. All right. So here again, you see that it doesn't look like our Pearson residuals are actually normally distributed. Okay, but maybe if I look at from this point, it looks like from this point I can draw a straight line to connect this. So here it's still not, I'm confused. Only some points are here that are not on the line, but I have some points here that are seems to be on the straight line. So what should I conclude? Is my model good or it's not good? All right, so that is the problem with diagnosis. You have to make a decision. Which is equals to 3, it's also another type of diagnosis plots, which we call Cook distance. And again, you can use this also for normal regression. And then here, the Cook distance is telling you whether they are outliers. Okay, so once you plot you look at this graph, it tells you that these observations, there seems to be outliers in them. So you can go back to your data and say that, okay, observation 931, observation 891, observation 2412 seems to be outliers. Okay, and then you can investigate them to see why they are outliers. And then you can have which is equals to 3, etc., etc. So the which is just telling you which plots do you want to produce? Which of the diagnostic plots do you want to produce? So which equals 1 means that I want the first diagnosis plot, and then the R software would produce it for you. Okay, so that is it about diagnosis. Very easy to get it from your logistic regression. Just use plots into brackets, the name of the model, and just change the which is equals to 1, which is equals to 2, and then you'll be able to interpret the values very well. Now, like I mentioned, using the plots, it's sometimes visual. The decision, it's subjective, you know. So the plots may be telling you, giving you some signs that probably there is a problem with their model, but sometimes you want to confirm whether the model is actually good or not. So you want to do some formal tests. So one of the formal tests that we have is called the goodness of fit test. And what the goodness of fit test that is that it tests the hypothesis that your independent variables are related to the outcome. So overall, are my independent variables, the gender, the age, the education, whatever that I put in the model, they are related to my what? My outcome. So that is my null hypothesis. So the alternative is that no, they are not. So if I reject the null hypothesis, that means that the two are not related. But anytime I'm fitting a model, I want to show that they are related, right? So it means that anytime I am making a decision on the goodness of fit test, then I want a goodness of fit test that is not significant. If it is significant, it means that I'm rejecting the null hypothesis, which says that my independent variables are related to my are not related to my outcome. But that is not what I want. I want to show that my independent variables are actually related. So anytime we perform a goodness of fit test, we want to get what? A non-significant p-value. So a non-significant p-value will tell us that our model is good. But a significant p-value for the goodness of fit test would mean my model is not doing well. Okay? And the test is based on the chi-square distribution. So how do I do that? The goodness of fit test, you can just take 1 minus, and then you compute the it perform a chi-square test like I mentioned. So you do a chi-square test from the null deviance minus the model deviance, and then you specify the coefficients. Let me see whether I have a simpler version. Okay, so I have the simpler version. So this is me trying to do the goodness of fit test by myself. So to do the goodness of fit test, I just take 1 minus, and then I compute the chi-square, where my degrees of freedom are based on this. But we can ignore that and just go to the simpler version, which is this. So anytime I want to perform that goodness of fit test in R, I can use the drop 1 function, specify the name of my model, and just say test is equals to chi-square. Okay, so when I do this, I'm testing whether all the independent variables are depends on the my response variable, and then I'll check whether that variable is significant or not. Now this gives you whether each one of them are related to the independent variable or not. So somebody had asked about how do you do a likelihood ratio test? This is more like a likelihood ratio test, where you now want to say that, well, the age group, is the age group related to the depression? Is sex related to depression? Is residency related to depression? Is hypertension related to depression? And so it gives you the likelihood ratio test, which you have here, and then it gives you all the p-values. Okay, so here the conclusion would be that it looks like hypertension is related. It looks like age group is related. Okay, it looks like residency is related at 1% level of significance. So I have some of the variables in my data that are related to my depression. So how do I conclude? It will still be very difficult for me to conclude because some of them are related, but some of them are not related. And that is why when I did the overall goodness of fit test, I find that the value is 0. Okay, I find that the p-value is 0. That means that I am rejecting the null hypothesis. So according to these results, the model that I am considering is not important. It's not a good model. Okay, and then the second part is telling me why it is not a good model, because some of these variables like gender was not significant. This one was also not significant. Only a few of them were significant. So I can make a decision that, okay, this model, there are some variables that are related to my outcome that I could consider. So maybe I could fit another model where I remove sex and I remove the wealth index because they are not important. Then I would perform the same test again, and then I would find that this time this model becomes significant. Okay, so that is the other goodness of fit test, the chi-square goodness of fit. You can perform it on each of the variable to see which one is related to the outcome. And the codes are very simple in R. They are just like one line of codes. Just they do drop one and then specify the model and just say test is equals to chi-square. It will give you the chi-square test for all the different variables. Then you can decide which variables are important and which ones are not important. When doing the likelihood ratio test, can it happen that you had example sex significant, but the test here shows it's not related to the outcome? That is not likely. If it is significant, then it must show here because this is doing one at a time. So drop one means that it's just looking at one variable on the response at a time. So it's not very likely that this is the case. So if sex is not significant, then when you come here, it would also again show that it's not significant. And we've already seen that when we did the descriptive statistics, we saw all the variables that were significant and those that were not. From the descriptive statistics that we had, we saw that this was not significant, this was not significant, hypertension was significant. What else? Age group was significant, sex was not significant. So you see that the result seems to be consistent with the descriptive chi-square test that we have done, that only hypertension and age group were statistically significant, but the rest were not. Okay. And then the last goodness of fit test is what we call the Hosmer-Le test. It's also a way to assess the goodness of fit of your model. And how it does it is that it compares your expected probabilities, that is the probabilities that we expect from what the actual one from your observed data is. And then it groups the data and compare the probabilities. So once it compares the probabilities, then if the model is good, then we expect that the expected proportions or probabilities and then the probabilities in the data should have to be the same. Okay. A question here: how would you go about a model shows a poor fit by goodness of fit, by all the variables in the model are significant? That will be almost it would also be surprising, but in that case, I'll still investigate to see why that is the case. The explanation could be that maybe there are other variables that are also very important that could have described the data well, but probably you did not collect that data. Okay, maybe there are some other variables. They are also very important. Not that so all the ones that you have collected, it is telling you that all the ones I have collected are important, but probably they are not enough to describe my data. So probably there are some other variables unobserved or something that you did not collect. They could be the reason why that model is not performing well. So it means that when you are redesigning your study, think about all the conceptually the factors that could affect depression and put them in the model. Okay. Martin, you can go ahead.
Thank you so much. On top of what you're explaining, so if this wasn't a pilot study where you've collected data and you're probably trying to see how the different variables are relating with the outcome, but you've done a complete study, and now you're at the point of data analysis and you're seeing that your model is not doing well, but the variables that are in there are all significant. So would you recommend going ahead to publish such results in a journal, or how would you make such decisions regarding that kind of data?
Yeah, so in that case, I mean, you cannot go back to redesign your study, but you can put in a recommendation that the model was still poor, like in terms of your goodness of fit test, you identify that the model was poor. So you recommend that maybe all other factors that could influence the response are important. It doesn't mean that the ones that are already there are not important, because that is why they are in the model, and that is why they are significant, and that is why you should report those ones even in your journal. So it means that they are important. You can still publish them because they are showing significant results. So they are just adding to the knowledge about those variables. So it should not be a problem at all. If it's a secondary data or data that you have just completed the study, you cannot go back and redesign. But then it means that it informs how the next study should be conducted. That what are the variables that are important that I need to add anytime I'm redesigning my study, so that maybe my model fit can be very, very well done. I hope that helps. Okay.
It does. Yeah.
All right. So the Hosmer-Lemosher test, it's also another goodness of fit test. And like I mentioned, the null hypothesis is saying that the expected probabilities and the observed probabilities are the same. So that is what I want. I want the observed and the expected probabilities should be the same. So if I reject it, then it means that my model is not doing well. So here again, in the goodness of fit test, I'll always pray that my p-value is not what? Significant. So that if my p-value is not significant, I'll be concluding that the expected proportion or my model is doing very well. All right. So that is that goodness of fit test. And in the to do the Hosmer-Lemosher test, I can use the library resource selection, and then I can perform the test. Okay, Hosmer-Lemosher test, and then I specify the model, my outcome, and I compare that with the fitted model, and then I specify G is equals to 5. Now that is one of the limitations of the Hosmer-Lemosher. Here you would see that it is giving me a p-value that says that it is not significant. So it means that my model is doing very well. Okay, that my model is doing very well, right? But then when it's because I have only divided my data into 5 groups, and I'm comparing the probabilities. So one disadvantage of the Hosmer-Lemosher that this can be very subjective, because I can decide to divide my data into any group at all that I have. But if I use probably the optimal number of groups, maybe I would have found that this this value here is not significant. So it's one way of also testing whether our model is yielding significant results, or it's a good fit or not. But that is the limitations that you encounter. How do you divide the data into the groups? If the groups are smaller, or should we have big groups or large groups? This is one limitation. So anytime you are using this kind of test, always remember that there will be questions about how did you determine what's the group, the number of groups? How did you determine the number of groups so that you are able to compute the expected probability for each group versus the observed probability for that same group? Okay. And then one also nice thing about the Hosmer-Lemosher test is that you can actually also plot it. You can also do a plot, and in that plot you always expect that the blue line would be on the same straight line. Okay. And then we can use the ggplots package. I'll not go into this. You can just use the code. You can always use this code to replicate any logistic regression that you want to fit. You can just replicate that, because the important thing is how did you fit your model. So you just specify the results of the Hosmer-Lemosher, and then you can run this particular test. Okay. We are not doing well with time. Joel, are we continuing, or we can stop here for today? I think we probably would need 4 sections to finish these slides. 2 more sections to finish this slide, because we are almost halfway through the slides. So that means that 2 more sections we should be done. We have one scheduled for Friday.
Yes.
Yeah. Okay, so maybe we'll need maybe one more sections if we plan to go to the slides, but let's see how far we can go on Friday.
Okay, great.
All right, I see some people are already having other meetings, so maybe this is a good point to start to stop and process all the things that we have learned today, so that we can build upon this when we meet again on Friday. We are not meeting tomorrow because I have other engagements, but Friday should be fine. Yes, Florence, your hand is up. Please go ahead.
So thank you. I had written my question in the chat, but it's like I've not seen it. I was asking that when I have a case where the primary exposure of interest is not significant, what do you do? Do you go on and include it in the model even if it's not significant, or what do you do?
Yes, so I was going to come to that later on, but it's good that you have brought that discussion up here. That the goodness of fit tests has statistical things. It's things that statisticians have created, you know, so that it can guide you in some of the things that you are doing. So I may have a variable that is not significant, and we'll see it later on when we are doing variable selection. So we've already seen one, like using the goodness of fit test to test whether this variable is related to the outcome, yes or no. All right, but there are some variables, and they are the reason why you have conducted your study. Your exposure variable, for instance, it is the reason why you are doing the studies in the first place. So if that variable is the main primary variable of interest, and you want to see its effects on depression, if you remove it, then you don't have any question to answer anymore. You only say that it's not significant. But what you can do is that you have to, even though a variable may not be significant, but if biologically or based on your public health knowledge, that variable is known to be associated with the response, or it's one of your primary research question of interest, then you have to consider that rather than the statistic, what the statistics is telling you. And again, it's the same for the p-values. P-values can be significant because your data is very large, but it may not be because the variable is actually related to your outcome. And that is why most people do not like interpretation of the p-value, but they rather would report the confidence intervals where you look at the effect sizes rather than whether it is significant or not. So it's the same debate even when we are performing model diagnosis. There is no straight answer when it comes to modeling, but the important thing is that you have to know how to justify every decision that you have made when you are doing your model building. And that is why I'm taking you through this, so that you understand the advantages and disadvantages for any of these procedures, so that when you are interrogating your models, you consider them or you think about them even when you are making your decisions. So should you remove the exposed variables if it's your reason for conducting the research, even if it's not significant? If it is not very significant, still leave it in the model, report it as not being significant, add the other variables that you have adjusted for, tell them that those ones are still related to your outcome, and then you can make some findings out of it. I hope that helps, Florence. Okay, great. Is there any other last question? If not, I think this is a good point to stop. The number is going down, so I guess people have other engagements, so we can stop here. Martin, your hand is raised. Let's have your question.
Thank you. I still wanted to add on to what Florence has asked. Mine is regarding statistical significance versus the importance of that variable in the model. Sometimes you can run an analysis, and then some variables may not be statistically significant, but when you add them to the model, they can improve maybe your R-squared for linear regression or the pseudo R-squared. So sometimes it's hard to make a decision. I just wanted to hear from you what your guidance would be. If a model improves the R, maybe the R squared or adjusted R squared, but it's not statistically significant, what would be your take on such a variable in a model?
Okay, sure. So it depends on the situations. So that is why it's good to have a variety of methodology in your toolkits. Okay, so probably that model, the variable is not significant. Let me use a regression as an example. If you are doing regression and then you add a variable that is not significant into your multiple regression analysis, every time your R square would increase. So anytime you add a model, you add a variable, the R square automatically will increase. And so an R square is not a good measure of telling you whether your model is good or not. So that is why we have what we call the adjusted R square, which will penalize for adding more variables, such that if I add more variables, the variable would be penalized, and so that even it will tell if it's not doing very, if that variable is not so doing very well, then the adjusted R square will not go higher. It will only go higher if indeed that variable has an effect because of that penalization. Okay, so that is one. So it would, my answer to you would be that it would depend on what type of metric you are using to decide whether adding the non-significant variable is improving your model, yes or no. If it is on logistic regression, we are going to R square, and then that is where here I see a lot of people make a lot of mistake when they are talking about R square. You will see, we will see later on that in logistic regression, your R square does not make any sense. All right, or it does not give you the type of interpretation you get when you are doing linear regression. Okay, so we'll discuss that into details the next time we meet. So if I am using R squared to make a decision on whether it has improved my model or not, I have to be very careful when I am I'm making that decision. And we will talk more into details of R square, which we call the pseudo R square, when we meet again on Friday. Does this help, Martin?
Yes, it does, but I wanted you to also, you just hit on what I was very interested in, the adjusted R squared for a linear regression. If this variable is improving, maybe whenever I add a particular variable, my adjusted R squared goes up. But this variable shows the p-value is not significant. Would I retain such a variable on such a ground? Or there are some other parameters that I would check for me to decide whether I should retain it or not?
Yes. So in that case, so what I'll do is that there are other metrics for assessing whether your model is doing well or not. Okay. So it's possible that you could add that, and then R square would adjusted R square would increase. But have you checked the bias that introduces into your model? So there are other metrics that you have to look at. So let me use regression as an example. We have what we call DF betas. We have what we call DF fits. Okay, so I will have to look at all the different metrics that help in determine whether my model is good or not. My R square, my adjusted R square may go up, but then that variable probably would have introduced some bias into my results. And so I have to be very careful. I have to look at the improvement of the adjusted R square vis-a-vis whether it is introducing some bias into my model or not. Okay?
Yes, thank you.
Are you okay with that?
Yes, that's fine.
Okay, yeah. So we could, if I was taking you through regression, it's diagnosis and stuff. It's some of the things that are very well where we could see some of these discrepancies, but then we can look at all the other metrics as well, so that we can make a determination. But yeah, unfortunately, I'm just focusing on GLMs. Probably in the future, or maybe the person who will be teaching regression on this course probably could add some diagnosis so that you look at the range of metrics that are available to determine which model is good or not. But in case you have any questions, you can also drop me a mail and I'll respond to it if you have any questions that probably we are not able to address here. Okay. All right. The number is almost done. So, thank you all for joining today. I wish you all the best and see you on Friday. Bye.
Okay, bye bye everyone. See you tomorrow.
Bye bye.
See you Friday, sorry.
Thank you. Bye.